In today's presentation, we'll be focusing on Ekman Motion and some applications. In 1893, Norwegian explorer Nansen set out for the Arctic. Few had tried before, but this time he used a different method. Nansen had a specially built Fram that would be stuck to the polar ice, which would be moved by ocean currents towards the North Pole. However, he had failed. What Nansen noticed was that while the winds moved the ice, they were moving at an angle to the wind direction, about 20 to 40 degrees. As we see here, Ekman was tasked to find out why this was. Ekman rightly speculated that this was due to the Coriolis force, created by the Earth's rotation. To show this, he imagined the oceans as thin layers stacked upon another. When wind blows over, friction between the air and the water would cause the surface layer to move. As the surface layer moves, energy can transfer to the lower levels, moving them as well. However, with each successive layer, the movement is slower due to friction of the layer above. The Coriolis force acts on each layer, deflecting it to the right in the northern hemisphere and to the left in the southern hemisphere. Each layer deflects from its previous layer, creating a spiral, like so. This is called an Ekman spiral. Here's the view from the top. As we can see, because it deflects so much, some layers will be 180 degrees to the original wind direction. Because of this, if you were to sum up all the layers of the water, what you'd have is a net movement 90 degrees to the original wind direction. And as we've seen before, it would be 90 degrees to the right if it was in the northern hemisphere, and 90 degrees to the left if it was in the southern hemisphere. According to Ekman, the top layer should move around 20 to 40 degrees, which is what Nansen saw. The Ekman spiral has a depth. The depth is given by the square root of 2 times V over F, where V is the eddy viscosity, which measures the turbulent mixing of water layers, and F is the Coriolis parameter, representing the effect of Earth's rotation at a given latitude. The shape of this movement is given by the equation. And there are two key things about this equation. We have one, the negative exponential, which is a decaying function. So that means that the magnitude decreases with depth. And we also have the spiral, which is given by the cos and sine functions. You can think of the imaginary as just another axis. As we've seen before, the net movement of water is 90 degrees to the wind direction. This is called Ekman transport. When you have wind acting along a coast, you're going to have Ekman transport bringing water away from that coast. As the water moves away, we're going to have water from deeper layers rushing in to fill in that space. This is called upwelling, and it brings water from deeper layers. This water brings in a lot of nutrition, making these areas very productive. For downwelling, this is the opposite, where we have the Ekman transport bringing water towards the coast. This means that the deeper waters, with all the nutrition, moves away, making these areas less productive. Here is me blowing over a bowl of water with some vinegar added in. The vinegar sits at the bottom, but as I blow over it, it rises back to the top, showing upwelling. During the summer, me and my friends were fortunate enough to visit the small island called Madeira. The island was very beautiful, from towering mountains to sandy beaches. But there was one thing that we noticed. It was very windy. These winds create a lot of upwelling, and as we know, this brings a lot of nutrients. From a paper I found called Modelling the Hydrodynamics and Water Quality of Madeira Island, Portugal, it was shown that the southern regions or the coastal areas had very high productive areas with a lot of phytoplankton. This means that there's going to be more fish around those areas, and that is true. Fish is the national dish of Madeira and is very common in its diet. This is just one of the high productive areas in Madeira. Thank you for watching my presentation, and I've hoped you enjoyed it.